So let's look at this function, and let's analyze it graphically. First of all, if you set this thing equal to 0 and you solve it, which you've done in the past, then what you're finding are the what?
Aren't you finding the y of
the x-intercepts?
Oh, the x. Yeah.
The x-intercepts of that graph is what you'd be finding.
Okay.
If you set that graph equal to 0 and solve it. Now, it's not easy to do that in this case because it doesn't seem to factor very nicely, and so there's different ways to do that, and I'm not going to do that right now. That's not what this is about. This is about just generally concepts of it. Now, if you take the derivative of this, taking the derivative of that function, which you can just use the power rule, right? 4x cubed plus 10x minus 9. If you set that equal to 0, what does that help you find?
I don't know.
It helps you find the max min points of f of x. It helps you find the max and min points of that function.
Okay.
Because remember what the derivative means. The derivative is the slope of the tangent line. The slope of the tangent line at each point on f of x. That's what the derivative is. It's the slope of the tangent line. So if the slope of the tangent line is 0, that means that it's a point that line has a slope of 0. So that means the graph, the original f of x, I should have made that green. That means that f of x right here, at that point, that the slope of that tangent line, the tangent line is the red line there, that slope is 0. That means that point was where it stopped increasing or decreasing and then started doing the opposite thing. Right, so that just means that the slope of the rate of change was 0. The rate of change at that particular point was 0.
Okay.
That's what the derivative, the essential, that's calculus 101 right there. If you take the double derivative, change the color on this. If you take the double derivative of that function, f double derivative, now that equals 12x squared plus 10. That thing, the double derivative, if the double derivative setting that equal to 0 tells you where you have inflection points. It tells you the inflection points of f of x. So again, it goes back, and that when we take the double derivative and set it equal to 0, that gives us information about the original function. That's important, namely the inflection points, where the point changes concavity. That's what an inflection point is. So let me just give you a more basic example. All right, if I had f of x equals, I'm just going to come up with the easiest example I can think of, and I'm just going to make it up as I go. That's a cubic, right? And what are the zeros of that cubic? Let me multiply that out. I get x squared minus x, plus x minus 2 times another x. So I really just have x cubed plus x squared minus 2x. That's what that graph is, right? So that graph right there, x cubed plus x squared minus 2x. X cubed plus x squared minus 2x. That graph had the zeros of -2, 1, and 0, right? -2, 1, and 0. Those are my zeros for that graph, right? Is it opening up or down? I'm sorry. Is it going up from left to right or down from left to right? Because it's a cubic, right?
Yeah, I've kind of forgotten.
The positive leading coefficient means it's going down on the left and up on the right.
Okay.
So I know that graph is doing something like this. So it's just doing something like this.
Okay.
Right? Ish. Could be steeper than that, but that's sort of the essence of it, okay? So now let's take the derivative of this. f prime of x equals, now let's use this to find the derivative, right? It's easier than using this, right?
Yeah.
The derivative of that's going to be 3x squared plus 2x minus 2. 3x squared plus 2x minus 2 is what kind of a shape?
Oh, that's a parabola.
It's a parabola, that's right. And if I graph that parabola on there, on the same graph right here, see this point right here, that max point right there? That's related to a 0 of my derivative. See that min point right there?
Mm-hmm.
That's related to, if I go straight up to the x-axis, that's going to be where my parabola hits the x-axis. Because when I set that equal to 0, I'm finding, remember what I said before, I'm finding the max min points of f of x.
Mm-hmm.
So if I set this equal to 0, I get the max. Here's a max, relative max, right? And here's a relative min for that blue graph, f of x graph. So what would my graph look like? Well, is it opening up or down? This.
It's opening up.
It's opening up because the leading coefficient is positive, right? So it's something like this. That's something like what your graph is doing.
Okay.
Okay?
Mm-hmm.
All right, now let's find the double derivative. The double derivative is going to be what kind of a graph?
It's just going to be a line.
It's going to be a line,
linear.
right? This was cubic. This was quadratic. This is linear. It's going down by 1 in degree. And what does this equaling 0 represent?
It's going to represent.
Remember what I said before?
Yeah.
It represents an inflection point of f of x.
Okay. What's that?
What's that? Good question. Well, what is that value right there? It's x equals negative 1/3, right?
Mm.
X equals negative 1/3 is right here. It's the min point of your derivative, and if you go up to that point, that's 1/3 right there. That value right there, and what was it? It was 6x plus 2. So the slope is pretty steep. 6x plus 2. It's a steep line.
Mm.
But the important thing is it goes through the x-axis at the same place on the blue graph. You see the blue graph right there?
Yeah.
If I could zoom in, which I can't on this, but that blue graph right there, that point right there is where the graph changes from concave down to concave up.
Oh.
That's your inflection point.
Okay. All right.
So that point right there, that value was 1/3 comma something. The 1/3 I found from the double derivative, setting the double derivative equal to 0, gave me the inflection point of my original graph.
Okay.
The inflection point is the point where it changes concavity.
Okay.
So that's kind of a summary of what derivatives are all about.
All right.